Well, I have to say it is such an honor to be here in this audience. I am not a meteorologist. I don't even play one on TV. I'm merely an engineer. So this is really incredible, and I've learned so much over the last 3 days. I hope to be able to apply some of this as we start our exploration venture to the moon. So I'm going to talk to you about the moon, but the moon is just a stepping stone as we start to explore the rest of the solar system. And I hope my graphics can compete half as well with Luca's. So we'll start off.
3, 2, 1. Boosters in ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
So across the globe, all of our nations and industry are embarking on a new era of exploration, and we're going to go where no human has been before. So you're seeing the moon, and yes, humans have been to the moon, but now we're going to go to different locations. We're going to go to the South Pole and to the lunar far side. And we're not doing this as one. We're doing this across the entire globe. Multiple agencies are looking at this. And then from the moon, we carry our exploration goals forward to land humans on Mars. We're going to take what we've learned at the moon, what we've demonstrated, what we've operated, and translate that to Mars so that we can land humans there and start to explore. From Mars, we go on to the rest of the solar system. But to go, we have to be able to navigate our trajectories. We have to navigate once we insert into an orbit, our landings, and our traverses. And all of this is going to help us sustain life on all of these celestial bodies. So, of course, this audience is fully aware of the role for accurate measurements at Earth. So we'll just consider the second, the meter, and the kilogram for now. A lot of this talk will focus on the second, and that's because time and accurate knowledge of time and its distribution is key. It's critical for all of our agriculture, for our mining, for our drilling operations, for our infrastructure, such as our power systems, our electric grids, our water and our sewage supply systems, our financial transactions, our cell service, our data centers, our internet, and of course, navigation, be it on land in our various modes, as we look at the sea, in our shipping channels and logistics supply, or as we go towards the air and we go from one location on the Earth to another. And we have to do this safely and consistently. And this also applies to space, especially now as we start to have proliferated low Earth orbiting constellations. Now, the science isn't actually the driver for knowledge anymore. It's space situational awareness. We have to have good navigation. We have to be able to predict our states well to avoid collisions with other space vehicles. And for that, we have navigation. And the navigation that we're using most of the time is radio navigation that relies on time. And time, as we've seen, is the fundamental for our global economy. Well, one of the objectives for the moon is actually to develop a lunar economy. And in order to do that, we're going to have to rely on time. Our next objective, though, is interoperability. So we are going to seek that through standards, and we work through international standards, fora, and organizations to establish interoperable standards. So already the missions to the moon have begun in earnest by several nations. You'll see a collection here, and by many commercial ventures as well. So they've been pretty exciting times as we seek to explore the moon, and we've really seen how navigation is going to be critical to all of this, on all of these adventures. It's a very challenging environment at the moon, and we don't have the infrastructure that we've come to rely on Earth. So we have no canonical reference, no foundational elements. We have no time realization. We have no communication systems in situ. We have no position navigation systems in situ. No infrastructure like an electric grid. And, well, at least we don't have them yet, but we are working on it. So why is navigation at the moon so difficult? Well, first of all, let's think about spacecraft. It takes a lot of energy to launch a spacecraft from Earth up to anywhere, really, to just escape Earth gravity. So we have to be considerate of size, mass, and power. We have to make sure that we're flying things that are lightweight, that are small in size, use minimum power. And as we start with human exploration, all of these things have to be safe and space qualified and rated for human exploration. So as you know, and you can see from this image, although it was supposed to have Earth in the background, the moon is much smaller than Earth. And we know from the Apollo astronauts that that was actually a challenge because the horizon was closer, and they didn't really think about that ahead of time, so that changed their whole perspective. So that's one challenge. Another challenge is the lack of atmosphere. You might think that that's a benefit, but it's really a challenge because we're going in areas that have really low elevation angles to the sun. So the South Pole, the sun is very low in the sky, and the lighting is very, very stark. So that presents another challenge. Couple those two together, and vision-based navigation becomes not really reliable. So many of the space agencies got together, and we decided that we really need in situ radio navigation so that we can have our foundational elements and we can do our path planning to get to targets that are in the distance. And this is going to form our basis for navigation, whether it's in orbit or on the surface. And PNT, position, navigation, and timing, is going to form the basis for science, for our traverses, for our exploration, for making sure that we arrive at the correct location, and the many visioned activities that we see at the moon and creating habitats. And in order to perform radio navigation, we need exquisite knowledge of time. Exquisite is sort of relative here, and I don't mean relativity yet, but it's relative because we're not looking at parts in 10 to the 18th yet, but we're looking at exquisite in terms of space qualification systems. But the challenge is, how are we going to do time at the moon? What are we going to do to support all of these exploits? What does it mean in terms of time's impact to safely working and habitating on the moon? And what is the role of time on Earth, UTC, as we start these explorations? And I think what's critical here, and we've heard a lot about all this week, is that we have to maintain the SI second. Whatever that definition is in the future, we'll take it. And we're going to try to maintain that. And this means that we have to establish a time scale at the moon because beauty is in the eye of the observer here. So in order to maintain the SI second, we have to account for this guy, again, special and general relativity, when we're on the different bodies, right? And we have to be able to trace our time system, wherever we are, back to Earth. So we're going to use this new lunar time scale to inform our explorers and our industrial and our scientific endeavors of time at the moon and try to identify exactly how to relate it back to UTC. So we're going to establish time through the SI second, establish the meter, the kilogram, and these are going to be part of the foundational metrological units that we're going to carry forth as we explore. We're going to apply them. We're going to leave it to other people to try to measure them. And so it's vital to engage the international community to develop the standards for time through the BIPM and for all who are involved to heed to those definitions. This is really essential for safe exploration. And as we look to sustained human presence, it's essential to developing that lunar economy that we seek. And we may deploy clocks on the moon, and then we can test them out, make sure they work, carry that forward to Mars, where we can start to explore and go beyond into the rest of the solar system. But we have to evolve all of our systems. And because even though right now we are still dependent on Earth, we have to become more independent of Earth. We can't break the dependence, but we can kind of open the chain a little bit, if you will. Part of what we're seeking to do is to make sure that we can have continuous operations. So we have to be able to handle occultations to Earth. We have to be able to handle long round-trip light times, right, up to 40 minutes at Mars, for example, out to further locations, you can just imagine. So those are they present challenges now in how we operate. But when you have humans involved, that's an even greater challenge because you can't wait 40 minutes to get that observation, process it, send it back up, and then execute your activities. So how do we manage these systems now? We have plenty of missions that are in deep space. And generally, these missions are one-off kinds of missions. They're very unique. And they aren't looking to integrate all of their operations with humans and robotics or anything else. So they're kind of these unique kinds of missions. So you'll see from everything from Voyager to New Horizons to Cassini and the James Webb Space Telescope to Perseverance on Mars, Parker Solar Probe, Bepi Colombo, and OSIRIS-REx, the asteroid Bennu. All of these missions are wholly reliant on Earth to do their operations. And during dynamic phases, yes, they may have some pre-planning on Earth for landings or touch-and-go maneuvers. But really what happens is they'll plan everything on Earth, they'll upload that command sequence, and they'll have limited autonomy or autonomous operations on board. And it's very limited and very critical events, and then they immediately get the information back down to Earth. So while all of these missions are relying on Earth, they're also constrained by Earth because there are only a limited number of ground assets, and we have occultations and the round-trip light time to deal with. So we have to figure out how to move beyond these constraints of Earth. So we're going to enter this bold new era for exploration, for human exploration, and that traditional means of operation has to change. We can no longer afford to have a ground station send a signal minutes and minutes away, have the onboard process transpond the signal, send it back down, measure it on Earth, process it on Earth, now figure out where you are and upload it to that spacecraft or to that human, and then execute your maneuver. It's a very, very slow process. So we have to change, and we have to make sure that all of our operations are timely to meet these human needs. And there are agencies working together to establish communications and position navigation timing infrastructure and to deploy a lot of cooperating assets, all based on standards for interoperability. And there are working groups that are specifically established to look at these interoperable aspects and make sure that we're all compatible with each other, no matter which nation is looking to perform these activities. So these new domains where we now need knowledge of time, we need to start considering all of these things differently than we have in the past. It's kind of like ripping the Band-Aid off, if you will. So we're going to start to build these ecosystems to try to maintain and sustain life on other bodies, and we have to become less reliant on Earth-in-the-loop operations. So the question for lunar time is currently underway. We need to define a lunar timescale. You've heard about that a couple of times this week. And that timescale has to be traceable to UTC. It has to be scalable to go from the moon to Mars to Titan or wherever else we seek to explore. It has to serve accurate navigation and science. And honestly, it has to be easy for the user community because the user community is our customer base. To enable that economy means we have to lower the barrier to that user, and so we have to make it easy for them to access time. So while we intend to voyage far, Earth is still our home planet, and we do have to tie back to Earth. Hence, we have to relate some of these observations and these critical events to time on Earth. And so we'll have to work through that as we look to further our exploration. But as all of our nations are increasing all of the initiatives towards exploration, we start to also see more integrated operations, if you will, humans and robots working together to develop these ecosystems off of Earth. And then real-time in-situ knowledge becomes desperately needed. So think of things like the Lunar terrain vehicle that's going and has to go over to a cargo, pick it up, and transverse it over to another side to prepare for crewed landing. Think of space situational awareness in orbit around the moon as we start to proliferate, and then on the surface as you're navigating through craters, boulders, rocks, hazards that you have to avoid, and other vehicles and assets from multiple nations. Landings and ascents for dynamic activities. And we're looking to do precision landings so that we don't disturb all the science that's around it. And then consider extravehicular activities, EVAs. So astronauts have limited oxygen, they have limited thermal capacity for heating and cooling, and they have limited time. Multiple objectives, you have an 8-hour EVA, and limited resources. You can't really spend your time kind of orienteering and trying to figure out where you are. You need to know where you are immediately. So it's critical also that we all share an understanding, a common understanding of time as we start to explore to make sure that we're all doing this safely. So which time scale we should use, whether we should use time at the center of the celestial body or time on the equipotential surface, that is all under discussion with the CCTF task group on moon time, and we will let them decide what time it will be on the moon. So we are on the opening edge of a new dawn of exploration. Truly we are. And we're trying to make discoveries about the universe, about the galaxies, with Luca's help. Our solar system, other planetary systems and their moons, our planetary system, and frankly, our humanity. And so accurate and consistent metrology and measurements are going to be really the need as we start driving forward to these integrated operations. And we want to be able to make sure that the science that we deploy is fruitful, that we start to uncover all of the mysteries that we're seeking. And the moon is a really pristine environment. It's great because the far side is called a radio quiet zone, and it's actually called the shielded zone of the moon. So our frequency allocations have to be selected so as not to interfere there. And I was thinking, as Luca was talking, that it would be great to build a sky on the far side of the moon. That would be really awesome. Then you could have very long baselines and skies. It would be awesome. So really, this is going to look a little different, I think, for metrology, because everything that we've done so far is very much Earth-based. Yes, we have GNSS systems and we have other spacecraft out there, but the actual calibration, the measurements, they're being done here on Earth. So what does it mean now to deploy clocks on the moon or on Mars? What are we going to do? How are we going to calibrate these systems? What does metrology mean now? So I leave that up to all of the metrologists here, and you tell the engineers how we implement it. So as we near the end here, wanted to take advantage of this opportunity to say that we really are on the edge of a whole new dream of how we do this and how we do this globally to try to look at exploration and science in a new way. And I think BIPM and other international organizations for standards are really the key here, because if they define the standards, then we will do it correctly, and we will all use those standards. And lastly, I want to take the opportunity to say, bon anniversaire to BIPM. Happy 150th anniversary. And thank you all very much for the opportunity to present here today. I hope you learned a little something about exploration. Thank you.